Reactance is a property of capacitors and inductors, and usually applies when these components are used in AC circuits. However, it does still apply in DC circuits. More on this later. At its heart, reactance is simply a way of describing how a capacitor or inductor impedes the flow of current around a circuit. Now you might be thinking, well, how is this different to resistance? And that's a very good question, so let me explain. Firstly, a recap on resistance. The resistance of a resistor is really describing the ratio of voltage across to current through that resistor, and this value is constant no matter the circuit that it is placed in. Reactance has two main differences to this. The first is that the reactance of capacitors and inductors is frequency dependent. This means that the frequency of the AC current will change the reactance of the components in a circuit. The second difference is that reactive components will cause a phase shift between the current and the voltage. So instead of them being in sync like this, one will get shifted to the right or to the left. So now let's talk about equations. The reactance of an inductor, XL, is given by XL equals 2 times pi times the frequency times the value of the inductor in henries. And the reactance of a capacitor is given by 1 divided by 2 times pi times the frequency times the value of the capacitor in farads. From these equations you can see two things. As frequencies get large, the reactance becomes large for an inductor and small for a capacitor. And as the frequency approaches 0 or DC, the opposite occurs, which gives the same result as our description for capacitors as an open circuit and inductors as a short circuit from DC circuits. The last thing to understand is that reactance is best represented using complex numbers, and we use impedance to describe the total effect on a circuit. By making a couple of changes to the equations, we get impedance as a complex number. A resistance would simply be a number that only had a real component. If you think of complex numbers as vectors, then these values have a magnitude and an angle of 90 degrees or negative 90 degrees, respectively, for an inductor and capacitor. The magnitude is the ratio of voltage to current, like a resistor, and the angle is the phase shift, positive for a leading voltage and negative for a lagging voltage. Now let's take a look at an example. Here we have a 1000 Hz source with a 100 ohm resistor and a 10 mH inductor. The impedance of the circuit is the value of the resistor plus I times the value of the inductor, which comes out to be 100 plus 62.8 I. In polar form, this is 118.1 with a phase angle of 32 degrees.